Good morning, everyone. Welcome to our NMIS Insights webinar on sheet metal forming simulation. Thanks for your patience while we just wait a few minutes until all attendees have time to connect. Thank you. Thanks again for your patience. We'll just start in 1 minute or so. Thank you. Okay, thanks very much. And I'll just hand you over to my colleague, Stephanie Craig. Thank you.
Morning, everyone. Thank you very much for joining us for part 2 of our forming team webinar series. So today's webinar will be presented by some of the senior modellers within the AFRC. We have Diego, Ilangavan and Hosan. So let's get started with some housekeeping. So the webinar is being recorded and will be made available on the YouTube channel, the same as the rest. Your microphones and your webcams will be turned off during the session to avoid any background noise. You can type your questions throughout the session into the chat and we'll get to them at the Q&A session towards the end. And we will obviously answer any questions that you have there. Any questions that can't be answered on the day, we will follow up after the event. And you can also use the hashtag NMIS Insights for any questions. On Twitter, it is at NMIS_group. And there will be a survey after the event, so please take some time to fill that out. So, for the people who don't know who we are, the National Manufacturing Institute, or NMIS, is a collective group of research facilities working together to transform the Scottish manufacturing landscape to become a global leader in advanced manufacturing. NMIS will, or we will, aim to reduce the barriers to innovation by enabling access to state-of-the-art facilities within a research environment. We will also aim to stimulate investment and increase the competitiveness of Scottish manufacturers and become a catalyst for job creation to strengthen the supply chain. We'll also work with manufacturing businesses from micro SME to large OEMs to create an opportunity for peer learning. We'll also use collective knowledge from the One Scotland team that I'll mention in a minute that will aim to attract and equip current and future workforce with the skills required to increase that business competitiveness. So as I mentioned, the One Scotland team, NMIS will be operated by the University of Strathclyde and will be supported by various strategic partnerships here that you can see on the right hand side. I won't go into too much detail about that just now. So who are the NMIS group? Well, the NMIS is made up of sort of 3 key elements. So under the NMIS umbrella, we have 2 specialist technology centres who are both open at the moment, one of which is here today, the Advanced Forming Research Centre, and the other is the Lightweight Manufacturing Centre, focusing on that composite material. In development as it stands just now is a temporary workshop space, and our outreach via our NMIS network is very much live just now via the Manufacturing Skills Academy. They are actively promoting a variety of courses that are available just now. And hopefully then in 2022, we will officially launch the National Manufacturing Institute building, which I'm sure a lot of you may have seen around the Renfrewshire area next to Glasgow Airport. So with that, I will now pass you to our first speaker, who is Diego Gonzalez, and he is a senior modeller within the AFRC's forming team. Diego.
Thank you very much, Stephanie. This slide contains the contents of the presentation. We will start with trying to summarize the benefits of the modeling for the industry. Then we will explain the general capabilities we have in the forming team in terms of modeling and simulation. And then finally, we will jump into 4 case studies where we apply these capabilities in simulation. We will talk about superplastic forming simulation and also the simulation of hydroforming processes. Superplastic processes, SPF and hydroforming are core lines of research within the forming team. And then the last 2 case studies will be a thermal analysis, and this thermal analysis will be applied to a forging system, and a CFD analysis of a water wheel. Thermal analysis of forming and forging systems and CFD analysis are more recent lines of work or lines of research we are working right now in the team. So if we jump to the next slide, I will briefly explain the benefits, just a flavor of the benefits of modeling for the industry. Okay. First of all, the most important benefits is obviously that the modeling is going to explain the kinematics of the sheet metal forming process. Okay, so SPF, hydroforming, all these forming processes are not easy to be understood. The SPF is a closed system. The hydroforming process is also a system difficult to be understood, because we close the dies and we don't know what's going on inside the furnace. We don't know what's inside the press during the process. We can have sensors there, but it's very difficult to understand what's going on inside the press once the process starts. So the FE simulation allows to the industry to understand what's going on there once the press is closed. Once you have a validated model, you have a so-called predictive tool. You can play with the model and propose changes and propose improvements to that process. Okay, and this is a key aspect, and this translates into a lot of benefits for the industry. This translates, for example, in less experimental trials, or if we optimize the process, we can have a reduction in cost or a reduction in time. Okay, we can find a better material selection for the sheet or for the dies, for example, cheaper materials, and we can also avoid premature failures. So these are just a few of all the benefits that simulation can bring to the industry. Okay, in order to take advantage of all these benefits, we need obviously good liaison between the people doing the simulation and the people working with the freshies, working with the system and in the workshop. And we do have this liaison, this interaction between teams within the FRC. In the next slide, if we jump to the next slide, I will briefly explain which are the general capabilities we have in terms of modeling in the forming team. We work with 2 types of software. We work with obviously commercial software, and we have bespoke software which is focused on forming sheet metal forming applications like PAMSTAM, for example. We also have general purpose software like Abacus. We have expertise in the implementation of Fortran subroutines, user element subroutines, or user material subroutines. Many occasions the commercial software needs to be complemented because you cannot find in the libraries the type of user element or material you need. So we have expertise in this type of Fortran subroutines, and we also have expertise in MATLAB and Python scripting. Okay, so in the image of the slide, we can have a general workflow of a simulation of a sheet metal forming process. We can start with a MATLAB script, for example, in order to obtain the values of the parameters of the model. Excuse me. We can then jump into the FE analysis. We can have there the commercial solver dealing with the equations of the problem, and we can have at the same time coupled with the FE solver a user subroutine to define the material for example. And then we can post-process the results by means of a Python script. Okay. We also have a good understanding of the FE method, of the finite element method, whether if it's implicit or explicit, and we are used to deal with the convergency issues. We are used to solve these convergency issues you can have where dealing with non-linear problems solved with an implicit method. Okay. If we jump to the next slide, we will explain briefly a bit of process modeling. In order to take advantage of the benefits I mentioned before, the kinematics, the understanding of the kinematics of the problem, the optimization of an industrial process, we need to have a reliable model. And this means we need to consider all the relevant aspects, all the relevant variables of the hot or of the cold forming process, whether if it's SPF, superplastic forming, creep forming, deep drawing, or hydroforming. We always need, obviously, to consider the relevant variables of this process. And we need to consider the friction, obviously, the exact value of the friction of the process, the initial blank shape, the material, obviously, it needs to be defined and characterized very precisely and accurately. All these relevant aspects needs to be considered in the problem. In the images of this slide, we have two examples of SPF simulation. In many occasions, the client asks to the forming team to come up with a optimization of the SPF process, and we find out the optimum pressure cycle in order to have optimum SPF conditions within the titanium material or the material of the SPF process. Okay, or in other cases, the client come to the facility asking for a temperature reduction with all the benefits linked to this temperature reduction in the process, less alpha case formation, cheaper tooling, and we need to find out the pressure cycle to proceed with this reduction in the temperature. This is just an example of how we proceed with SPF. Later on, my colleague Hosan will go into depth in the simulation of SPF analysis. The next slide will explain a little bit of the, if we jump please to the next slide, we will talk about the testing capabilities we have in the FRC. Obviously, the type of tests we do are linked or are based on the analysis needs. If we work with cold technologies, we will proceed with tensile testing, for example, in order to define the flow curves, to define the R values, the isotopic values. This is also available for warm conditions. If we work with SPF processes or forming hot forming processes, we will proceed with tensile testing at high temperature in order to capture the rate dependence of the material on the temperature. In terms of failure, obviously we need to know the limits of the formability of the material. We have the BUP testing based on Nakajima test samples, and coupled with this BUP test, we have GOM equipment and a digital image correlation approach. And obviously, when we need to validate the material, when we need to validate the simulation and the model, we can proceed with GOM scanning of the components and compare the thickness of the formed component against the results of the FE simulation, or we can compare the shape of the formed component with the FE results. In the next slide, we will briefly explain a bit of the material modeling. Obviously, the material models are critical to have accurate and reliable simulations. We work with advanced plasticity models, rate dependent and rate independent models. We have experience in anisotropic models, obviously. We work with kinematic hardening models like Yoshida-Mori to capture for example, the spring back phenomenon. PAMSTAM has this Yoshida-Mori model built in their software, and is really useful to precisely capture the spring back phenomenon. And we have expertise in microstructural based modeling. Hosan will talk later on. Just an example where we apply this microstructural based modeling to have an understanding of how the grain size evolves during an SPF example. Calibration of the models, of these plasticity models, is really important, and we do it through MATLAB scripting or by means of the math wizard of PAMSTAN, for example. We need accurate estimations of the parameters of the model, and when we talk about damage prediction, we also have expertise in this type of models, which evolve a damage variable for each individual elements of the simulations to define or to determine when we are going to have fracture. Okay, this is a line of research within the group, and we have colleagues working on this type of damage models. This approach is go one step beyond the forming limit curves. Okay, and in many occasions we define the damage variable using the stress to axiality factor within the variable of damage. And in the last slide, related to the material modeling, I will just briefly explain how we proceed with the anisotropic characterization. So in cold forming simulation, we need to precisely capture the anisotropy of the material. In many occasions, we have to deal with titaniums or aluminums or materials which have a lot of anisotropy. So we have a very good understanding of these anisotropic models, Hill family of models, or the Barlach family of models, Becher and other anisotropic plasticity models. And in order to define correctly which type of plasticity model we have or we need to apply for this specific material, we need to consider all the information available, all the information coming from the lab. So we will consider the yield stresses at different directions within the blank. We will consider the equibiaxial yield stress, and this is a very important aspect because we want to capture and to understand how the material behaves in an equibiaxial mode. Okay, when we form a component, we will mainly have plane strain and biaxial deformation modes more than pure tensile modes, and we will use also the R values, the anisotropic coefficients, and these will allow us to understand what type of anisotropic model we should be applying there. The material hardening, we will use the flow curves we obtain for the 0 degrees for the direction of rolling, and we can extrapolate these flow curves based on the biaxial flow curve, and we can define the material hardening in an analytical manner using a power law, a simple power law, or a bit more complex power law, or in a tabular way. So we have different ways to precisely capture the material hardening of the material and to introduce that in the simulation. And the last point to capture and to define this anisotropy is the calibration of the parameters. As I mentioned before, this is a very important point. We need to solve the optimization problem in a precise manner. And currently we use the math wizard application of PAMSTAN, which allows us to understand which model is the best for each specific for the material of interest we're working with, and it allows us to obtain the estimation of the parameters of this anisotropic model. We will jump now. We will jump now into the 4 case studies. So Hosan will explain right now the simulation of superplastic forming processes.
Thank you, Diego. Hello, everyone. Today I will take you through 2 case studies from our work in modeling of different processes. The first one will be about the modeling of superplastic forming process. Modeling the SPF process is required for many goals. One of those goals is, for example, the development of the pressure curve, as Diego mentioned, required to set the press to form the component. The whole steps from developing this curve, starting from the moment the die arrives till we have the curve, was described in a previous webinar titled Superplastic Forming Benefit and Challenges in our NMIS Inside webinar series. Hopefully you have attended this webinar. If not, you have a chance to view it again through our YouTube channel. One key step in the development of the curve is the finite element analysis and modeling the SPF process. To have an accurate FE result, the material should be well characterized to get the material parameters that will feed the material model used in the analysis. As Diego mentioned, in the FRC, we have those materials, testing and characterization capabilities to get those material parameters. We do high temperature tensile tests on our Zwick testing equipment. Tests can be done in argon environment and up to 1200 degrees Celsius. We need the material properties from two types of tests, the step jump test and the normal hot tensile test, to have the flow curves at different control true strain rates at required temperature. As a result of the various tests we completed for different alloys, we have a good expertise in testing different materials. Then once we characterize the material and based on the test result, we can define the optimal SPF conditions. In next slide, I'm going to show you how we use the material properties we had from the test to feed the material model and to calibrate the model to get its parameter. Next slide, please. As you see in the top right of the slides, there are phenomenological and microstructure rate-dependent material models that are well known and available in the public domain that we use beside other models to represent the material behavior. For example, the last constitutive equation captures the grain growth or the grain size evolution during the SPF process. This equation captures both the static grain growth by atomic diffusion due to the high temperature in the absence of deformation condition, and the other part of the equation captures dynamic grain growth, which is related to the material deformation. While the mechanical behavior itself is modeled by the viscoplastic response of the material, which is expressed by a power law-based model, for example, as in first equation. Then two steps are usually carried out to calibrate the material model and to model the material response during SPF. Firstly, the microstructural evolution is numerically analyzed by calculating the parameters of the last equation, for example, rho, phi, mu1, mu2. The fitting of the experimental data for the grain size is based on in-house developed MATLAB script. Secondly, the flow curves are fitted by using the grain size evolution data as an input to the constitutive equation in the top. Once the model is calibrated, it is then implemented into the FE package through subroutines. As a result, from the analysis, we can get the pressure curve, visualize the material deformability, thickness distribution over the forming component, thinning, and etc. That helps us to predict how will the final component look like and make us save a lot of trial costs that would have been spent if we try to form the material without modeling to understand its formability. Next slide, I will show you a case study for the SPF of Ti54M alloy, where a Ti54M alloy component is formed. Next slide, please. So we have here Ti54M titanium alloy, which is developed by our tier 1 member, Timet. This alloy has almost the same mechanical properties as the well-known Ti64. It can be deformed at lower temperatures than Ti64. Therefore, there is a potential for Ti54M to replace the Ti64 in an SPF application. You can see in the figures the thickness distribution of a component after being formed. On the right side is the GOM scanning result of the formed component, while on the left side is the finite element calculation. There's a good agreement between the FE result and the GOM result. This is one outcome we have from the analysis. We can also check the formability of the material at different stages during the process. We can also check the grain size of the component and etc. Therefore, and as I mentioned before, no need to spend money on trials to have some result, but through modeling, we can predict those results and save a lot of money. That was all about the modeling of superplastic forming process. And for now, I will pass it on to Ilangovan.
Thanks, Osam. Hello, everyone. So I'm going to talk about more of cold sheet forming process in the next few slides. Okay, so the case study is about the punch hydroforming of nickel superalloy. So for the benefit of the audience, I just want to give a brief introduction about the process. Okay, so what do you mean by hydroforming process? So the hydroforming process is a specialized forming technique that uses fluid pressure, for example, water or oil, to deform the sheet or tubular material to form a required shape. And there, excuse me, yeah, sorry about that. So the typical the hydroforming techniques the industry uses for the sheet forming process would be the cavity type hydroforming process and then the punch based hydroforming process. So today I'm going to talk about more on the punch hydroforming. So the typical material what the hydroforming process utilizes right now. So we could form the steel material, the aluminum, the commercial pure titanium, and then nickel superalloys. These are the typical materials which we could use the hydroforming technology to form. And the aerospace industries uses this technology to form very complex geometry. However, there are very limited use of this particular process in the automotive industry. So they can take advantage of the benefits coming out of the hydroforming technique. So for example, with the hydroforming technique, we could able to reduce the tooling cost, because if you choose cavity or the punch, so you will obviously end up with reducing the tooling cost probably by 30%. And then because of the reduced tooling development, so we could able to reduce the process development cycle time. So this is another benefit we could able to achieve. So the most important benefit we could see from the hydroforming process would be increased formability of the material, because unlike in deep drawing process, so we have two different tooling elements like punch and die. So whereas in the hydroforming process, we will have just one tooling element. Because of this, the friction between the tooling and then the sheet material would be, I would say, very, very low. So due to that, we could able to enhance the formability of the material. And with the process setup, we could able to achieve high precision of component. And it's mainly recommended for low and medium volume production. And just for the understanding purpose, I just want to give an explanation with a schematic. So as you could see, there was a punch, there was a movable die, and just above that, we have a blank. So there was an oil chamber on the top of it, and the rubber diaphragm, okay, so which will have a direct contact with the blank. So once the oil chamber moves, okay, so the die, the movable die moves at the bottom, and based on the punch geometry, the overall the dimension, the overall shape have been captured. Okay, so with the application of pressure. So this is how the overall hydroforming system works. So can you move on to the next slide, please? So this particular slide, it's mainly to focus on the part geometry. This is the case study which I'm going to discuss now. So we have a part geometry. So before we go for the process modeling, we will try to understand more about the part requirement, for example, thickness, and then any special feature requirement, for example, the top radius, the flange radius, etc. And before we go for process model, we will try to analyze the material as discussed in the previous section by Diego. So we do a lot of material characterization for the benefit of accurately predicting the result. So we do tensile testing mainly to characterize the work hardening behavior of the material, and then anisotropic behavior of the material. And then we use the bulge test, so mainly to capture the biaxial yield point, so which is very critical to develop a material model. And then the forming limit curve, it's mainly to assess the failure limit of the material during the process. And we follow some specific approach in order to identify an appropriate anisotropic model using an inverse FE approach. So there is an example you could see in the animation. So we try to simulate virtually and then try to identify an appropriate anisotropic model. So on the right hand side, so it's more about the boundary condition of the FE simulation. So we try to translate the learning from the experimental work, and then we will try to capture all the process related parameters into our FE model. So the kinematics, the friction condition, and the pressure, all these things I'm going to discuss in the next slide. So in the boundary condition, you could see there was a movable die, there was a fixed punch, and there was a blank. The pressure would be applied onto the blank surface. Okay, so the coining ring was used for some specific reason, and that would be explained in the next slide. Okay, so for the benefit of our customer, so we used to do a lot of iterations through design of experiment by considering the process variable, the key process variable, for example, the pressure, then the blank geometry, tooling, draw depth. Okay, so these are the process parameters we consider for our design variable. So for example, just for understanding purpose, okay, so when we increase the pressure during the forming process, especially the hydroforming one, so we stretch the material too much, okay, so due to that we may end up with rupture or even localized thinning. So we have to identify and optimize pressure value, so this is quite important. And in terms of defining the depth, defining a depth is also again an important parameter. Like if you want to achieve certain level of thickness in the final formed part, so the definition of such depth in each process step, it's quite important. And then depends upon the complexity of the part geometry, we need to define the number of process steps. And then so sometimes it may require heat treatment as well. And then so these are the typical process parameters we consider by doing a series of experiment. And finally we come up with a process definition, as you could see in the center of the slide. So we start with an blank geometry, and then we form the part with about 45 millimeter in the stage one, and then we introduced the intermediate annealing process, and then finally we form the second stage. So then finally we had introduced another process step mainly for the part requirement. Okay, so in order to achieve an consistency in the flange radius, we have introduced the coining process step. So, and in the right hand side of the slide, you could see the comparison of FE and then experimental work. So we could see there was a good agreement in terms of the thickness distribution for the formed part. And the overall, the key benefit achieved for our customer for this modeling work would be, so we could able to overcome the process related challenges, for example, wrinkling, thinning, cracks kind of issues that was overcome. And then as explained by Diego, so the definition of optimized pressure cycle for the hydroforming also, it's an important one. Okay, so otherwise we have to do more trial and error approach. It would be quite expensive and then time consuming process. And finally, okay, so by doing this modeling development, we could able to achieve the target geometry first time, right? So with that I will move on to my colleague Hosam. He will talk about thermal analysis further.
Thank you, Alan. Now I'll talk to you about another modeling capability we have in our team and currently have various projects on. It is the thermal analysis of forming and forging system. The main aim of this type of analysis is to help us identify the temperature over the system we are studying, whether it is tooling or studying the system itself. Also, we look for other outcomes such as the thermal expansion, thermal stresses distribution in the system. All those outcomes are very critical for designing the tooling or the system itself. It allows us to choose the right materials that can withstand the predicted temperature. In the thermal analysis of tooling, we consider the different type of heat transfer from convection to conduction to radiation. These types of heat transfer are reflected in the model by using different type of interactions and interaction properties such as surface to surface contact, defining the gap conductance using film radiation, surface radiation, or even cavity radiations. In the next slide, I will take you through a case study where we use the thermal analysis to help us designing the tooling for our Future Forge program. Next slide, please. So the Future Forge program in NMIS will be the world's most advanced hot forging research platform and will include a 2,000-ton hydraulic press. It's a tri-mode press which enable open die, closed die, and isothermal forging processes. In industrial scale, all of that on one press platform. As a part of the NMIS Insight webinar series, there was a webinar titled Future Forge, Shaping the Future of Hot Forging. It's available on our YouTube channel. If you would like to know more about the NMIS Future Forge program, I recommend you to watch it. Next slide, please. So here you can see one of the tooling we are designing for the open mode forging. We focus on maintaining the top surface of the tooling at target temperature for forging, whereas this top surface will be in contact with the billet to be forged. At the same time, we want to reduce the temperature at the bottom of the tooling as much as possible, where the tooling will be assembled with the press bed. You can see on the top right that we used 110 interaction to reflect accurately what's happening in reality. This will make us predict accurately the temperature distribution over the tooling. Then we can decide which materials can be used in each region of the tooling. We can use expensive materials with high thermal resistance in the hot region and cheaper material in other regions, instead of using one expensive material all over the tooling. Through this, we can save a lot of money, and that's why FE is very critical in designing the tooling. Next slide, I will show you another 2 examples of the tooling for the Future Forge program. Next slide, please. So as previous example, you can see that we were able to maintain the temperature at the top surface as a targeted temperature for the forging process, while the bottom surface temperature is reduced for assembly of the press bed. In those 2 designs, we are using 2 different design concepts based on our experience and knowledge that helped us to reduce temperature at the bottom of the tooling. That was me today, covering both case studies of modeling SPF process and thermal analysis of systems. I hope I was able to give you a brief introduction about some of the modeling work we are doing in the forming team. And for now, I'll pass it back again to Ilan Govan.
Thanks, Osam. So this is yet another case study which we would like to share. Okay, so this was recently developed for our new customer. Okay, so called Characters Water Wheel. So this particular work is mainly to understand, the key objective of this project is to understand the interaction of the wheel, and then to try to calculate the power and the efficiency of the wheel. So this is the main objective of the work. And then like following the development of a 2D CFD model, so we want to validate the result, and using a 1:10 scale model, and then gain understanding more about the wheel hydraulic behavior and investigate its performance. This is the overall objective of this particular work. Okay, so just for a quick introduction about the water wheel. So the Characters wheel is based on idea of harnessing both potential and kinetic energy by utilizing the change in the direction of momentum. And the novelty of this particular wheel design as gradual curvature of a blade design, which will allow to run the water smoothly without have any major impact, which we could able to see the conventional wheel design. And in the left hand side, you could see the boundary condition which we consider. So this particular mesh is primarily focused on the water wheel section. So there was a rotating mesh was considered, and then there was a center stationary mesh was considered. So with a very fine mesh, and the water inlet you could see. So we have introduced an velocity there, and then probably in the water outlet we consider pressure as the boundary condition. So these are all the overall boundary condition. So we consider 3 important strategy for this particular work. For example, multi-phase modeling. So through multi-phase modeling, we could able to simulate the phases of the water and the air interaction. And then we consider the turbulence modeling. So we had introduced an turbulent effect on the water just to be very realistic to interpret the real environment. And finally, we consider another technique called sliding mesh technique. So this would allow us to rotate the mesh of the wheel in the region occupied by the water. Okay, so this is the overall on the wheel, sorry. So this is the overall definition of boundary condition which we have considered. So probably I will share you the results in the next slide. Okay, so this is the animation video which I would like to share, and for the understanding, the blue color is the air and the red one is the water, and the combination of different color with a mixture of water and air with different proportion. And the key benefit what we achieved from this project was, as we know, the cost involved for the water wheel development and then the testing in a harsh environment, it's quite challenging. So we could able to simulate, and then we could able to correlate some of the experimental condition. For example, we simulated for 2 different flow rate condition, which was well correlated, and the fluid behavior also matched with the experimental work. And in terms of the experimental work, as well as we could able to see the kinematic energy observed in the torque curve, and the model was used to estimate the performance curve of the wheel, proving consistent efficiency of the process parameters. And finally, taking the learnings from the CFD model, we could able to work on modifying the process variables like the design variables like wheel diameter as well as the number of blades. So it would give good confidence for our customer in order to develop different range of wheel design. So with that, I'm going to complete my talk mainly on the case study. Now I will ask my colleague to continue on a few slides on testimonials as well as the questionnaires.
Thank you very much to all the speakers today. Unfortunately, I need to read this word for word because they are testimonials. So we thought it would be really good for you to kind of hear from the industrial clients that we've worked with. So all of these clients here have completed a body of work with us, with our team using the modelling and simulation software. So a Boeing representative said that the simulation work provided by the AFRC forming team added value to the project in hot forming. The insight coming from the FE analysis helped in reducing the experimental trials, but also bringing in a significant risk mitigation for the process to be implemented. Another customer, Timet, clearly the philosophy of the work that has been done will be used for development of SPF projects in the future. And Collins Aerospace, AFRC, has used its knowledge and expertise to provide deformation modelling services to Collins Aerostructures. These services provided useful data in several of Collins Aerostructures' development efforts. And lastly, from the previous case study from Langavan there, the Carruthers Renewables Company, working with the AFRC has exceeded their expectations. We are very pleased and excited by the results the CFD model has yielded, which gives us greater confidence to invest in a technology demonstrator on a larger scale. A big thank you to Team AFRC. Well, that is our presentation for today. Please feel free to take a picture of this slide. And for any NMIS related inquiries, you'll see the email address there. For any forming related inquiries, feel free to email myself. So now we will like to answer some questions. There have been questions flooding in throughout the presentation, and we will just get going with that. One question to the panel. Have you tried re-entrant shapes with hydroforming? I'll ask the panelists to unmute themselves and please answer the question.
So it would be better to understand like what exactly the question is all about. So I couldn't able to follow the question. Re-entrant shapes, I couldn't able to follow.
Okay, so let me see. We have PP date as the attendee. Could we unmute PP date?
That's him unmuted, Steph. PP date, if you want to just press your microphone button, it should work.
Yeah. So yeah, now is it okay?
Yep.
Yeah. So I just wondered how re-entrant shapes, whether you have tried re-entrant shapes. Re-entrant shapes means the shape where the bottom has got a higher diameter compared to the top. So the opening has got a smaller diameter. The bottom of the cup has got a higher diameter.
Okay.
Yeah.
Okay. So I followed your question. So I think for this particular design variable, okay, so we have to come up with an probably the process approach. Okay, so we worked on similar projects. Okay, so like it's come up with an IP, so we cannot share this information here. So we have this experience. Yeah.
Okay, and another thing I wanted to know was about the
pressure
values.
Okay.
Yeah, pressures for Inconel, forming Inconel at room temperature, because Inconel has got a very high yield point at room temperature. So what are the typical pressures for forming the forming under room temperature?
So again, we cannot share anything on the pressure value. So as you, it's mainly IP related information, I would say. And yes, okay, so we worked on those material as well. And probably there was some paper also published from AFRC. You can refer to those pressure values.
Maybe you can you share that paper?
Probably I will come back to you.
Okay.
Offline. Yep.
Yeah. So I'll type in my email address.
Okay.
In this.
Okay, thank you very much for that. We have, I think we had another question from yourself there regarding the friction factors. How did you get the friction factors between water and the wheel, Elangovan? Can you help with that?
Yeah, probably we cannot share at the moment, okay, because it's in final stage of validation, okay, so we don't want to share right now, okay, so these friction factors.
So is there any publication based on that?
Probably very recently we had published, not published, okay, so presented in a Hydro conference. Okay, so Hydro 2020, which is held online. Okay, so probably you can find some information. I
No,
doubt.
see, the thing is, it may not be possible for us to get access to that conference proceeding. So if you have presented, would you mind sharing the paper?
I will check with the right engineer to get those information, whether we could able to share it or not.
Yeah.
Okay.
Thank you very much, Langavan. Okay, so further question, which software do you use for SPF from Archit?
So for SPF, we use PalmStam, we use also Abacus. So we use both softwares.
Thank you very much. From Dr. Mohammed, can you use Yoshida model in warm or hot sheet forming using PalmStamp?
So for using PalmStam, we're using currently PalmStam mainly for cold sheet forming processes. Unfortunately, Diego just dropped out the call. We have some connection, but we can come back to you offline regarding the warm and hot sheet forming processes. But mainly we're using the PalmStam for the cold processes. Yeah.
So probably I can add what Wosam had explained. So right now we are developing the testing facility in AFRC mainly to support cold forming process. Okay, so the in-plane tensile compression test, and probably it was mainly designed for cold. However, we can potentially use by making some changes on the fixture for warm temperature material characterization as well. Okay, so but it has to be studied in detail. Okay, so we are working in this direction now.
Thank you, Elango. From Shivam, what software do you use and what are some of the core things to keep in mind for simulations to predict the shape, stresses and temperatures of the sheet?
So for softwares, like it depends on the process itself for we're modeling. So we use Deform, we use Abacus, we use PalmStam. And let me read Emmanuel's question.
The rest of it, what is the core things to keep in mind for the simulations to predict the shape, the stresses and temperatures of the sheet?
Usually like the material characterization is very important. You have to do a very good material testing and characterization to know well the material properties, because you will need these properties to feed your material model and to calibrate them. So material testing is it's a key thing that you have to take care of.
Thank you very much, Hossam. From Isai, hope I'm pronouncing that correctly. Are you planning to couple with machine learning?
So if I can reply with this one, like in the FRC, we have a digital team. So we can look in this in the future, but for now, we still didn't develop anything in here, but this is in our mind, yeah.
Thank you very much. Another one from Dumeti, it just says warm forming experience, assuming you mean what is our warm forming experience? Could somebody answer that?
So Langvan, you can jump in if you like after me. So we have some good warm forming experience. Like I cannot share a lot of information, but we did with some alloys doing a kind of warm forming of the process. I'm thinking about what type of information I can share, but like different alloys, we try to hydroform it at warm temperature. Yeah, we have this experience. Yeah.
I need to apologise to everybody.
Yeah,
A lot of the stuff we do is IP sensitive, so apologies if we can't answer the question directly, but do feel free to follow up. Another one from Dometi: how do you use failure criterion for hydroforming? Alangavan, do you want to try that one?
Yeah. So see, the failure criteria for hydroforming, we use the regular forming limit curve, which was generated from using the Nagasima test. So that would be used for our validation.
Thank you very much. Another question from Archit: how do you calculate the grain refinement during the forming process?
So if you're talking about what I've described in this SPF, usually we do, after we do the testing at the required temperature, required strain rate, everything, we check the microstructure and we know what is the grain size, and we can track the evolution of the grain size. Then using the material model as described before, we try to calibrate this model and get the parameters depending on this experimental data. So that's how we trace this grain evolution during the SPF process.
Thank you, Hossam. Dometi Raja Satish has raised their hand. Could we unmute them, please?
That's them unmuted, Steph.
Thank you.
Hi, thanks for your presentation. I had a few questions. How do you use the failure criteria for hydroforming or any other forming process except the cold forming? Because I've been working on forming limit diagrams from years, but we don't have a valid hydroforming curve to use in simulations. But how you would if you have a proper failure criteria, the whatever we are predicting is all goes in vain. I think I don't know. Just curious about how you use the failure criteria. I don't think we can use the cold forming limit diagram, which we usually read for other different materials, either in hydroforming or hot forming. So just my question is, thank you.
Okay, so see in the hydroforming, okay, so we are considering the cold hydroforming process. I know what you are trying to say in terms of whether we can use the FLC for the cold hydroforming or not. Okay, so because of the friction condition which was considered for the FLC. However, from an industrial perspective, so these are the readily available testing practice which we can use it, and it can be validated during the experimental trial. Okay, so we use FE simulation and then we do experimental trials in order to compare whether the used FLC curve were intact with our requirement for the material. So, and additionally, we are working on some advanced damage models as well. Okay, so probably that also could help. Okay, so for the future modeling approach. Okay, so this is how I could see, because in order to answer the industrial requirement, this is the immediate option available. Okay, so however, it has to be validated for each material by doing the experimental test.
Thank you.
Stephanie, don't know if you can hear me right now.
Yes, we can, Diego, yes.
Okay, great. Sorry, I lose my connection from my PC, so I'm calling from my phone. I lost part of the questions. I just reading the chat 2 questions during the presentation. I was just to briefly explain that. Though I don't know if Elango or Hossam jump into that. So just to complement a few things. I read what software we use for SPF. We could use, or we have used in the past, Abacus. Right now we're using, or we are looking to use PumpStan. I think mainly we have 2 advantages when we work with PumpStan, where we have SPF simulation. One is that PumpStan, we can use an explicit method, and this is a great advantage. We avoid convergency issues, and the explicit method of PumpStan is a great advantage when using or when we're dealing with SPF simulations. 10 years ago, 15 years ago, not too many people will think in explicit methods applied to long long processes like SPF, 1-2 hours duration. Explicit methods were more applied to quick processes or crash simulation of crash simulations or quick processes. Right now, there has been an advance in this line of simulation, and I think this is a great advantage to use an explicit method with the correct, obviously, time increments for SPF models. Sorry, for SPF simulation. The other second advantage is the remeshing aspect. So we can start with an initial element size of, 5-6 millimeters, and the software PAMSTAN by itself will refine the element in those areas, in these curvature areas, these fillet radius where we need small element sizes, okay? Obviously, without going without going below the thickness value of the sheet. So I would say these are the two benefits of PAMSTAN in SPF simulation. Another question I heard, and I'm sure it was answered, just a comment, just in case it wasn't answered, was about softening or grain size refinement in SPF. Okay, we have an example in the presentation. Josam explained in the presentation an example where we were working with optimum SPF conditions. So we always have grain size or an increment in the grain size because we work in these optimum SPF conditions for the titanium or whatever the material we have. Okay, you expect to have grain size increment, or even the same grain size using the simulation. But if you go to non-optimal SPF conditions, you can have dynamic recrystallization, so you can have these material softening. So in this case, we need to include a third term in the differential equation of the grain size evolution, where we split or where we reduce the grain size. And as it was explained, the key element is to have the testing data. At the end of the day, we rely on the test data, on the data coming from the workshop. We need to know, apart from the testing, the flow curves, we also need to know the grain size evolution. So we need microstructural information about the grain size. So we are very used to couple the FE simulations with testing in our labs and microstructure analysis also in our labs. In this case, to know how the grain refines due to dynamic recrystallization. And this is introducing the differential equation by means of a third term, which diminishes or decreases the grain size. And we will introduce dislocation density in order to know when and how we will trigger this dynamic recrystallization phenomenon. So it's just two points I wanted to comment before I lost my connection. Sorry about that.
Thank you, Diego. That's no problem. We have time for one more question, and I think you might all recognise who it's coming from. A question from Nicola Zueli. Hi all, will the AFRC have a material parameters database available from experimental characterisation of a range of or some of the materials which can be used for modelling purposes when actual batch material data is not available? Would one of you like to answer, Nicola, please?
I can answer that if you want that. Josam and Elango can complement that. We already have that library, though obviously there is, depending on how we obtain this material data, there is IP linked to this data. So we know how we have this material characterization. In many occasions, we cannot apply that directly into a commercial project because there is some level of IP sensitivity on that data because it comes from also a commercial project, so we cannot apply that data. In other occasions, ourselves, we decided to characterize materials, Ti64, for example, or the titanium materials or aluminiums by ourselves without having a specific commercial project, so we can make use of this data. Okay, we always try to rely on this material database if there are no IP issues, obviously. We understand that the data coming from the literature, the material data coming from the literature is okay, but if possible, should be the last source or the last source of information. We prefer, if possible, to do ourselves the test. In many occasions, the first work package in the project is to test the material in our labs. Okay, if we can apply the data, the information from our database, we will apply that. If we cannot apply because we don't have that material database or because there are IP issues, we will propose to the client to proceed with testing in our labs, and I think this is the best option in many occasions.
Thank you very much, Diego. Hopefully we answered all your questions today. If there was anything that we couldn't answer for you, please feel free to get in touch on the details below. As I said, please feel free to take a picture of this slide and contact us directly. Thank you.
Thanks everyone for joining us today. Hope you enjoyed today's webinar. Thanks also to our speakers, Stephanie, Diego, Elangovan and Hossam. Shortly after this session, you'll receive a survey, and we'd be most grateful if you could take a few moments to complete this. Your feedback does help us shape future webinars. Our next NMIS Insights is next week on Wednesday, 9th of December, and is about 3 projects offering free assistance to smaller Scottish manufacturers. If you'd like more details on this, you'll find it on our website at nmis.scot. And I'm just going to bring this webinar to a close now. Thanks very much for joining us.